Alright, what I'm going to do here is introduce you to a topic that I was going to leave until the next unit, but decided that due to the difficulty of the next unit, and actually just the amount of information that we'd get started with this, ideally what I would have you do is do this in an actual lab, give you some components, have you try to figure out the relationships between different things, but that's not going to happen. And it's too risky for me to just let you do it on your own, even with the virtual lab. I do want you to play around. Hopefully you will play around and see different things. And I'm going to give you a challenge, I believe, next week on setting a particular type of circuit up. But I need to show you some basics first. What we've done so far is just one resistor, one battery, wires, that type of a thing. What we need to do is be able to deal with multiple resistors. So the first thing I'm going to do is get a battery here. And actually, let's just handle the battery right off the bat. If I get a voltmeter out here, and I go ahead and I attach voltmeter there, and actually I've got them in the wrong order. I can tell by the negative sign. Doesn't really matter too much, but I go to one terminal and the other terminal, I get 9 volts. If I have two in series with each other, this is in series, connected one after the other, then we get 18 volts. So it's really, I think it's a pretty straightforward relationship with batteries. What I'm going to do is I'm just going to reset all of that, and we'll get another battery back here again. Next thing that we're going to do is I'm going to take a wire and I'm going to hook up a resistor. Oops. Okay, so I've got one resistor here, and it's just your classic light bulb. And I'm going to hook up a wire here. And actually, let me do it this way. And I'm going to make it a little bit more complicated than it probably needs. Actually, you know what? I'm not going to make it more complicated than it needs to be. Let's keep it simple. So I now have 2 light bulbs. There we go. And they're on. Now one of the things that I can do is I can take this, right, and I can connect it there. Now one of the things that you'll notice is that this is just your simple circuit. We've got a battery, we've got electrons leaving the battery, going through the light bulb, and then going back to the original terminal of the battery. And it completely bypasses this part because there's nowhere for it to go. Oops. Now if I do this, the chargers have now 2 obstacles to get through. So these tungsten filaments, most light bulbs, or the incandescent light bulbs, you see a few of them nowadays, but the incandescent light bulbs have these tungsten filaments. They're very thin, and they're made of tungsten, which is not as good of a conductor as something like copper. So the combination of the narrowness of the filament and the resistivity of tungsten causes it to have a fairly high resistance, particularly when compared to a wire. So, or the normal wires that we would use. But what I want to draw your attention to is the fact that we have these 2 light bulbs, and they're clearly not as bright as when we just had one. So the first thing I'm going to do is pull out my trusty little voltmeter, and I'm going to actually change this. Let's just change it to 10 volts. So that'll have a very slight effect. I'll check and make sure everything's good. The electrons are being attracted to the positive terminal, repelled from the negative, so we have a voltage drop across the battery of 10. Now if I connect to the sides of this light bulb, we see that there's a voltage drop of 5, and over here we see a voltage drop of 5. So we have 5 volts being used up through this light bulb, and we have 5 volts being used up through the other light bulb. And that probably is not a terribly surprising result. We put 2 resistors in series, they each are going to use up about half of the energy that's there. I'm catching on something. Hopefully that wasn't too irritating for you, noise-wise. In any case, we have this tool that we can use to get what the voltage is. Now what I want to do is kind of redesign this a little bit to include an ammeter. Okay, now through the magic of the pause record button, I've prestoed this fairly complicated circuit into existence. So let me just go through and explain. We've got our battery. It is 10 volts, just like before. And we have two light bulbs. They are 10 ohms, just like before. Some differences here. I have ammeters at some key locations, places that might be of interest. Maybe I should have put one in here, and actually I think that I might just do that, just so that we can be absolutely certain that the things are working out how we want them to. As you'll see, it's not really necessary, but we'll do it anyway, because the charges are leaving the one side and they're entering in the other side, so we might as well just check and see. And I'm actually going to hide those electrons for now. So we have our ammeter set up all over the place. We have these switches. Okay, now the way that the switches work, actually I'll unhide them so you can see this. What I'm going to do is I'm going to close one of the switches. So I've closed that switch, and you can see that the charges move on through and they complete the cycle. And one thing that we notice is that the current appears to be the same absolutely everywhere. This should not be a surprise, okay, because whatever goes in has to come out somewhere. So if we put charge into this ammeter, it's got to come out the other side. That's the only really realistic option. If that doesn't happen, that means that we're starting to load up on charge in the ammeter. It's going to become a charged object. And what we know about charged objects is they apply forces to charges. And so once it starts to become charged up inside there, it's going to push the excess charge out. So you never actually wind up, if you have good conductors, you never really wind up with an imbalance of charge. Now, one thing that we can also see is that the voltage through the wire elements and through the ammeters are zero, which is exactly what we would expect. Where it starts to get different is if we look at two different sides of the light bulb. So we can see that we have a voltage drop of 10 volts there, and we have a voltage gain of 10 volts through here. And that's just the basic gist of it. I should actually, if I'm being strictly speaking technical about it, I should do it like this, so that my order of probes is identical. Okay, so the red probe is the one where the electrons are entering. And I'm doing this a little bit backwards, but we'll do the red probe there and the black probe there at the exit end, and we have negative 10 voltage. If I do the same thing here, where the black one is at the exit end and the red one is at the entrance end, I get plus 10 volts. So we gain 10 volts going through here, we lose 10 volts going through the light bulb. Now, this is not that exciting because I only have the one loop. Whoops. One thing that I can do is I can open up this switch and I can close this other one. And one thing that you should see immediately is that this is very bright and I have 1 amp through everything. And actually, let me just hook this up across here as well. Okay, so we're reading the negative 10 volts. I'm going to open up the switch. I'm going to close this one. And now you're going to see a bunch of different things. First of all, I still only have one loop that's functioning. Okay, and we can tell, even if I hide the electrons, we can tell because this ammeter is reading 0 and these ones are reading 0.5. But I can also tell that something has changed. The light bulbs are not very bright. And there's two good reasons for that. One is that with twice the resistance, we're only getting half the amount of current. We're also only getting half the amount of energy per charge used up. So we're getting half the number of charges moving through the filament at any given point in time, and we're getting half as much energy available per charge to be used up in this resistor, because the other half of the energy that they're given, the 10 volts total through the battery, is being used up at this other resistor. So this is the basic idea with resistors in series. This is called in series because the charge has to travel through both resistors. It has no alternative. It can't find some sort of a shortcut to get back to where it wants to get to. So the basic gist of it is that if we have two resistors of equal size in series with each other, it's going to double the resistance. Okay, what we've done is effectively double the resistance here. Just briefly, because I don't want to take up too much time with this, what we're going to do is I'm just going to change the resistance of these light bulbs. So I'm going to make this one, instead of being at 10, let's make this one at 5. And this one we'll make at 15. Now, one of the things that you'll notice is that the current through the system remains exactly the same. What I've done is I've taken 20 ohms of resistance, and instead of splitting it up evenly with 10 and 10, I've put it at 5 and 15. One of the interesting bits here is that it appears that the larger the resistor, the more energy is being used up across that resistor. And that shouldn't be too much of a surprise. If you have a hard obstacle to get through followed by a short obstacle to get through, you're going to use up most of your energy on that hard obstacle and only have a little bit less for the easier obstacle. Or vice versa. If you start off with the easy obstacle and then go to the hard one, you're going to do the same thing. You're going to kind of not use up that much energy with the easy obstacle, and then you're going to spend the rest of what you've got on the hard obstacle to try to get through there. And that's exactly what the charged particles do. Now, how do they know to do this? How do they know how to divvy up their energy? That's kind of a more advanced topic, and we don't quite have time to get into it. Now, one last thing that I want to show you is, because I have this set up so nicely and we've got this switch here, actually, before we do that, let's just take a look at the voltmeter. I've been looking at the ammeters, and I haven't been looking so much at the voltmeter. So this was our 5 ohm resistor, and remember we have 10 volts total, right? So our battery says we've got 10 volts. If I look at this, then this one says 2.5 volts are going to be used up across this light bulb, and 7.5 volts will be used up across this light bulb. Okay, and if you think about the ratios of the resistances, this kind of makes sense. You use Ohm's law, V equals I times R. The current's the same throughout. You can't have a stacking up of charges anywhere. So we have the 0.5 amps, we multiply it by the resistance, we get the voltage. So we're using up most of our energy here. The last thing that I wanted to do is just show what happens when I close the switch. Okay, so this one goes out and this one becomes super duper bright. The reason for this super duper brightness is because, first of all, it's a pretty small resistor. It's only 5 ohms, and I've got a 10 volt power supply, so that leads to 2 amps of current that pass through, and all of the energy per charge is going to go through here. If we look at the electrons, you can see they're going quite vigorously right now. Okay, and the ones over here in this second loop aren't doing anything. What we've done effectively here is create a short circuit, so it doesn't matter whether this one here is open or closed. The charges look at this situation and they're like, well, wait, this one offers absolutely no resistance at all. This one offers a lot of resistance. Why would any charge in the right mind go through this route when this requires no energy to go through this sort of middle line? That's it for now. We're going to continue this discussion with a different type of circuit where the resistors are not lined up in series, they're going to be lined up in parallel. And this, what I've just shown you here, is kind of a prelude to that idea of resistors in parallel, and you'll see hopefully the similarities.